వాటర్ పెట్టలా తీసుకో. Good evening. Good evening. Good evening. Okay, thank you. Right. So listen. So last day we started solution to the state transition matrix. Solution to the state equation we discussed. What is the solution to the state equation? That is x of t equal to Laplace inverse of Si minus A inverse into x naught plus Laplace inverse of Si minus A inverse B into U of S. This should be remember. The second one is, remember STM, state transition matrix. Phi of t equal to e power at, that equal to Laplace inverse of Si minus A inverse. Okay, be remember this. Okay, phi of S equal to what? Si minus A inverse. This should be remember, so that you can solve the problems related to solution to the state equation. Okay, note down one problem. Obtain the complete time response. Obtain the complete time response. Obtain the complete time response of the system given by x dot equal to 0, 1, minus to 0, x plus x. X not equal to y equal to x. Come on, get the answer. Get the solution. First of all, what is the given state model? Homogeneous or non-homogeneous? So x dot equal to ax, na? It is x dot equal to ax. That means it is homogeneous state equation. Homogeneous state equation. Because input u equal to 0. What is the solution for homogeneous state equation? Input 0 means 0 input response. The solution is simply x of t is nothing but 0 input response. ZIR. Simply 0 input response. ZIR. Okay, na? Y of t how to find? Complete time response means y of t. First x of t how to find? That x of t substitute, then you will get the y of t. So first you have to find the 0 input. What is the 0 input response? Tell. E power at into x naught. E power at into x naught. So first e power at. So that is called pi of t. Even this can be written as pi of t into x naught. So now first find STM, that is called pi of t. Find phi of t. That equal to what? Find phi of t. That equal to what? E power a t. That equal to Laplace inverse of Si minus a inverse. That equal to Laplace inverse of adjoint of Si minus a by det of Si minus a. Adjoint of Si minus a by det of Si minus a. So now write Si minus a. You write Si minus a. So here x dot is given. I'll write the matrix here. I'll write the matrix here. What is x dot? Tell 0, 1, minus 2, 0. Here x. Come on. Now find it. Si minus a. How to get Si minus a? So Si minus a. Add S diagonally. Change the sign of coefficients. S sign become minus 1 plus 2. S diagonally change the sign minus 1 plus 2. This is called Si minus a. Now write adjoint of Si minus a. You write adjoint of Si minus a. Adjoint of Si minus a. So adjoint means diagonally change. Yes. Opposite sign means here plus 1. Here minus 2. So this is called adjoint of Si minus a. Now find pi of t. So write pi of t. Pi of t equal to Laplace inverse of adjoint by det. Individually write. Adjoint what happened? Yes. Plus 1 minus 2. Yes. By det. Det individually write to all the terms. What is the det? S square plus 2 na det. S square plus 2. S square plus 2. S square plus 2. S square plus 2. That equal to Laplace inverse of. So S by S square plus 2 means what? Inverse Laplace transform. It is like S by A square plus A square, na? Yes or no? That means what I can write? Cos of inverse Laplace transform. Apply inverse Laplace transform. What I can get? Cos root 2t. Here 1 by root 2. Sin root 2t. Apply inverse Laplace transform. This is minus root 2 sin root 2t minus root 2 sin root 2t. This is cos root 2t. So this is the what? This is the state transition matrix. This is called STM. Either it is correct or not means we can verify the properties. We can verify the properties. First property very easy. Pi of 0 should be I. It's up to t equal to 0, you should get identity matrix. T0 substitute 1, 0, 0, 1. That means it is an identity matrix. This is called pi of t. Next, what you have to find? X of t you have to find. Pi of t into x naught. Find ZIR. Find x of t. That is called ZIR. ZIR equal to e power 18 into x naught. ZIR you find. So that means what is ZIR? Cos of root 2t. So next 1 by root 2 sin root 2t minus root 2 sin root 2t. Next cos root 2t into x naught. What is x naught? Tell. X naught is nothing but what? What is x naught? X naught is 1, 1. X naught is 1, 1. Here I written a ZIR into x naught. So write x naught. X naught is 1, 1. Then write the answer z of t. X of t, right? That is cos root 2t plus 1 by root 2 sin root 2t. Next minus root 2 sin root 2t plus cos root 2t. Cos root 2t. Next, get the y of t. Next, get the y of t. This is called x of t. So y equal to what? What is y? Tell. Y equal to 1 minus 1 x. 1 minus 1 x. 1 minus 1 into x. This is called x. Now come on. 1 minus 1 x. What is x? Cos root 2t plus 1 by root 2 sin root 2t. Then minus root 2 sin root 2t plus cos root 2t. Come on, now product this, you will get the answer. Cos root 2t plus 1 by root 2 sin root 2t minus minus plus root 2 sin root 2t minus cos root 2t. Cos cancel. Find the here LCM and then root 2 22. 2 plus 1 3. So I think 3 by root 2 na. 3 by root 2 sin root 2t is the answer. This is called y of t. This is the complete time response to the given system. So like this, most of the time they are asking STM only. Most of the time they are asking only STM. So practice STM. Even ZIR, ZSR also practice it. Okay, na? Next one. One more problem is solved. One more problem. Find the following. Find the following to the given STM. Find the following to the given state model. To the given state model. Find the following to the given state model. First one, STM, state transition matrix. Second one, ZIR, zero input response or transient response. Third one, ZSR, zero state response. Fourth one, state transition equation. State transition equation, or simply it is called state equation. Both are same. Simply it is called state equation. Next, fifth one, output equation. Output to the unit step input. State transition equation. Output to unit step input. Output to the unit step input. Come on, do it. Write the state model. I'll write the state model here. X dot equal to 0, 1, 0, minus 3, x plus 1, 0, u, x not equal to minus 1, 3, y equal to 10x. Come on, do it. First, find the STM. Find the STM, Guruji. First, find STM. So, pi of t, that is e power at, that equal to Laplace inverse of Si minus a inverse. That is Laplace inverse of adjoint of Si minus a by det of Si minus a. Det of Si minus a. ठीक है? Now tell, come on, first Si minus a. What is Si minus a? Add S diagonally. So here S plus 3, opposite sign minus 1, 0. Now come on, find pi of t. Pi of t equal to L inverse of adjoint, diagonally change, S plus 3. Here S, here plus 1, 0, divided by det. Det is S into S plus 3. S into S plus 3. S into S plus 3. Now solve it. S plus 3 cancel. S cancel. Then find pi of t. Come on, Laplace inverse of 1 by S. S equal to 0. Partial fractions you find. S 0 means 1 by 3. So 1 by 3S. S equal to minus 3 means minus 1 by 3 into S plus 3. Next year 0. Here 1 by S plus 3. Come on, apply inverse Laplace transform. Find pi of t. Pi of t equal to 1 by 3 into 1 minus e power minus 3t, 0, e power minus 3t. This is called pi of t. That is STM. That is STM. Next. Second bit, what you have to find? ZIR. Second bit, you have to find ZIR. ZIR to pi of t into x naught. Pi of t into x naught. What is pi of t? 1 by 3, 1 minus e power minus 3t, 0, e power minus 3t, into x naught. X naught is minus 1, 3. Now get the answer. What is the answer? 1 into minus 1 means minus 1. 3 cancel. Then 1 minus e power minus 3t. Next 0, 3 e power minus 3t. Plus 1 minus 1 cancel. Sorry. Minus e power minus 3t. 3 e power minus 3t. This is called ZIR. Next, find ZSR. Third bit. ZSR. That equal to Laplace inverse of pi of S, B u of S. Pi of S is what? Si minus A inverse. Si minus A inverse. So this is pi of S, na? So this is pi of S. What is that? Si minus A inverse, where it is? This total is pi of S. This is pi of S. This is pi of S, and then Si minus A inverse pi of S. So this is pi of S. So write as it is pi of S. So pi of S you write. So ZSR equal to Laplace inverse of 1 by S into S plus 3, 0, 1 by S plus 3, pi of S into B. What is B? 1, 0. Into B na 1, 0. Into B 1, 0. Into U of S. U of S is unit step input na mention na. Dekho, unit step input. So write 1 by S. Now simplify this. Laplace inverse of. Come on. So first 1 by S. 1 by S into S plus 3. 0. 1 by S plus 3. Now product these two. 1 by S 0. Now get the answer. L inverse of 1 by S square 0, 0, 0. That means what you are getting? T 0. This is called ZSR. Next, fourth bit. State transition equation or state equation. That is called X of T. X of T equal to what? ZIR plus ZSR. X of T. State transition matrix different, state transition equation different. Equation means ZIR plus ZSR. ZIR plus ZSR. What is ZIR? Minus E power minus 3t, 3e power minus 3t. This is T. Both add it. Then you will get the answer. And 3 minus E power minus 3t. 0 plus and the same thing. 3e power minus 3t. This is called state transition equation. X of T. Next, find Y of T. Last one. Find Y. Y equal to what? 1, 0, X. So 1, 0, X. So 1, 0. X is what? T minus E power minus 3t. 3e power minus 3t. So that equal to answer is T minus E power minus 3t default. Is the answer. That's all. So remember the formulas, automatically can get the answer. You remember the formulas, automatically you'll get the answer. Okay. Okay. First element will be U of T, right? Laplace inverse of 1 by S is U of T. First element means, what is the meaning of first element? Where, in which bit? In which bit? U of T. First element will be U of T. Right. Unit step mentioned, na? Unit step is mentioned. Okay. Right. Next. So like this, you have to solve it. One problem, do the homework. In STM, where is U of T? Where is U of T? In STM. Here you want to write U of T. You can write it, nothing wrong. You want to write it, you can write nothing wrong. Right. Next one. One homework problem. Solve homework. Repeat above problem. Repeat above problem. So x dot equal to -2, 0, 0, -1, x plus 1, 1, u, x not equal to 0, 0, y equal to 1, 0, x. Do homework this. Okay. Here initial condition 0 means initial states 0 and 0 state response. You go by procedure, you will get the answer. Okay. You solve it. Next, controllability and observability. Next one, controllability and observability. Okay. Mention unit step na dekho. I told also, I show you. This is the question. Find the following state model STM, ZAR, ZSR, state transition matrix, output to unit step input. So that means input should be considered unit step mentioned here. Dekho ek bar unit step input. ठीक है ना? Hello? Karthik? Karthik? Okay, right. Mention unit step input. Otherwise, how can I substitute there 1 by S tell? Right. Next, controllability and observability. And observability. This is also important. Controllability, observability also important. This topic also important. What is the controllability first of all? What is the observability? Listen, Bhaiya. What is the controllability and what is the observability? Listen. Okay. What is the controllability and observability? Listen. What is the controllability? Means if you take any system, it's having some initial conditions. You take any system, it may be 0 or it may be some value, anything, x of t naught. It's having some initial condition. By applying controlled input u of t, by applying the control input, the initial states are changed to the desired state. 1 minute, just 1 minute. Right. So here, if you take any system, it's having some initial conditions. You take any system, x of t naught, it's having some initial condition. By the controlled input, the input states, the initial states are changed to desired state. In a finite time interval, initial states are changed to desired state in a finite time interval, then it is called controllability. Changing initial states to desired state in a finite time interval is called the controllability. Changing initial states to desired state by the controlled input in a finite time interval is called the controllability. For example, see, I'll take a simple RC network. I'll take. For example, listen. For example, you take simple RC network. Here VC naught is, for example, 1 volt. VC naught is just 1 volt. I'll apply here controlled input is 10 volts. For example, here 10 volts I'll apply. 10 volts I am applying. My desired state is 8 volts in a time t equal to t1. My desired state is 8 volts in a time t equal to t1. If this 1 volt I am able to change to 8 volts in a t equal to t1 duration by using this input, the VC naught I am able to change to 8 volts in a time duration of t1 seconds, then I can say the system is what? Controllable. If it is not changing these initial states, then we can say it is a what? Uncontrollable. If it is not changing, then uncontrollable. Okay? When the states change, there should be a continuity from input to this capacitor. For example, here discontinuity is there in the path like this. You apply infinite duration, the capacitor cannot charge. Then the states are not changes, then it is called uncontrollable. One way controllability gives the continuity. One way controllability gives the continuity from input to states. One way controllability gives the continuity from input to states. If the path exists, then we can say it is a controllable. Otherwise, we can say it is a what? Uncontrollable. Okay. So this is called the controllability. And what is the definition of controllability? Tell. What is the definition of controllability? A system controllability. A system said to be controllable. A system is said to be controllable. A system is said to be controllable. If it is possible to transfer the initial states, to the desired states, if it is possible to transfer the initial states to the desired state in a finite time interval, by the controlled input. Then we can say it is a what? Controllable. Changing initial states to the what? Desired state in a finite time interval by the controlled input is called the controllability. If the signal flow graph given, SFG is given, to check the controllability, to check either signal flow graph or block diagram, to check the controllability, observe the path, observe the path from input to states, If path exists, then it is controllable. If path exists, then it is controllable. That's all. Next, come to the observability. What is the observability? Listen. Observability means if you are able to determine the states of the system, in a finite time interval, then we can call it is a what? Observability. Okay. See, by observing the output, listen, by observing the output, if we are able to determine the initial states of the system, if we are able to determine the initial states of the system by observing output, by observing output, if we are able to determine initial states of the system, if determine initial states of the system, initial states, then we can say it is a what? Observable. Then we can say it is observable. When you are able to determine this initial states, there should be a path from what? Capacitor to output. If a capacitor to output is there, then by observing output, I can determine this initial states. In case here discontinuity is there in the path, then what happened? Can you read this initial states? Output not connected to the storage element. Can you read the what? What is the voltage across that storage element? We cannot read. Then we can say it is unobservable. One-way controllability and observability gives the continuity from input to output. Input to states is called controllable. States to output is called observability. Observability belongs to output. Controllability belongs to input. Input to states is called controllable. States to output is called observable. One way it gives the continuity from input to output. Okay? So that means what is the definition of observability? A system is said to be observable if it is possible to determine initial states of the system. If it is possible to determine initial states of the system by observing the output in a finite time interval. In a finite time interval, then it is called observability. So if you are able to determine the what? Initial states of the system, then it is called observability. What is the controllable matrix? So first we'll solve one problem, note on the problem. One problem. Find the K value. Find the K value to become the uncontrollable. Find the K value to become uncontrollable. Draw this diagram. Come on. Find the K value to become the uncontrollable. Come on, Guruji. Come on. Find the K value to become uncontrollable. K equal to how much? -1. K is -1. See, here states are there. For example, here I can take states x1. This is x1 dot. Here x2. Here x2 dot. So uncontrollable means no path exists. To become uncontrollable, no path exists. Between input to states x1. That means K plus 1 must be equal to 0. Why? Because if input is signal is coming this, then the states are going to be changed. In case no path, then what happened? No states are changed. That's why K plus 1 equal to 0. K equal to what? -1. K equal to -1. Here signal flow graph is very clear. So paths are very clear. That's why we are able to write the answer directly. Sometimes what happen in the exam, that fellow will give zigzag manner. That means, for example, like this, you will put a path like this. Different paths you will put it, or from here to path, somewhere some path they'll put it. Then they will ask the controllability. Then what happen here? They'll put here like -1 something, they'll put it. Then what happen here? If you observe physically path visible, but if you write the equation, that will become 0. And already it is 0. So physically path exists, but sometimes what happen? Due to many paths, here the summation becomes the 0. You observe just path exists, controllability is wrong. That's why don't follow this procedure. Don't follow this procedure. Just for idea's sake, I told. If it is clearly visible, then you can follow it. There are many paths like this, different paths are there. Better what you do, you go by column and test. You go by column and test. What is the column and test? I'll tell. Listen. You go by column and test. So write it. Column and test for controllability. This is the best for controllability. Columns test for controllability. I told how to write ABC matrix to the signal flow graph. Already I discussed now how to write ABC matrix. So once you are writing ABC matrix, then you can write you can check the controllability. Column and test for controllability. That is called QC matrix. QC equal to B, AB, A square B, and so on. A power n-1 into B. B, A, B, A square B, and so on. A power n-1 into B. When it is controllable, tell. When it is controllable, rank of QC equal to rank of A. Rank of QC equal to rank of A. Don't check the rank, just verify the det. Det of QC not equal to 0. You verify this enough. Det of QC not equal to 0, then blindly we can say that it is controllable. You just check the det. Not 0 means you can say it is controllable. Not 0 means automatically rank will be satisfied. Verify that enough. So then you can say controllable. Next, observability. Next, observability. Observability. Column and test for observability. That is Q0. Column and test for observability. Kalman test for observability. That is Q0. What is the Kalman test for observability? Q0 equal to C transpose, A transpose, C transpose, A transpose square, C transpose, and so on. A transpose n minus 1, C transpose. That equal to, we can convert transpose and row into column. That means I can write C, CA, CA square, and so on. CA power n minus 1. Next, det of Q0 not equal to 0. Rank of Q0 equal to rank of A. Then it is called observable. Now note on the problem. Check the controllability and observability. Check the controllability and observability. Check the controllability and observability to the given state model. X dot equal to 0, 1, 0, 0, 0, 1, minus 2, minus 3, minus 4. Zero, zero, 2. And y equal to 1, 0, 0. Come on, do it. Come on, Bhaiya. QC not equal to 0. Come on, check it, all of you. First controllable matrix, QC. So 3 by 3 matrix na, up to n minus 1. 3 minus 1 means 2. So first B, yes or no, first B should be there. Then AB should be there. A n minus 1, n is 3. 3 minus 1 means 2. So A square B. So B, AB, A square B. 3 by 3 means 3 by 3 only will get. Come on. B, what is B? 0, 0, 2. Next, find AB. B means 0, 0, 2. Next, find AB. A product with B. A, this is A. This A matrix product with B. A product with B. So 0 plus 0, product it. Row into column, row into column, row into column. 3 elements you will get. 0 plus 0 plus 0 means 0. Next, second row, 0 plus 0 plus 2 means here 2. Third row, 0 plus 0 plus minus 8. So that means minus 8. That's all. Next, A square B means A into AB. A square B means A into AB. A into AB. Again, A product with AB. Same A product with AB. Product the before column, write the next column. Product before column, write next column. Product before column, write the next column. Come on. 0, 2, 0. That means here 2. Next, 0, 0, minus 8, minus 8. Next, 0, minus 6, minus 6 plus 32. That means plus 26. That's all. Now check the debt. What is the debt? Debt of QC equal to, so 2 into like this. This will be 0. This is minus 4. That means minus 8. Not equal to 0. So controllable. Next, check the observability. Next, check the observability. Check the observability. Q0. Q0 what? C, CA, CA square. First C you write. What is C? 1 0 0. 1 0 0. Next CA you do it. CA means here C is what? 1 0 0. This product with A. C product with A. Row column, row column, row column, row. First 0 0 0 becomes what? 0. First element 0. Next, next second column, same row, second column. Now tell 1 0 0. That means 1. Next, third, come on. Third one you calculate 0 0 0. That means what? 0. Next, CA square means CA with A. CA with A. CA is what? 0 1 0. So you write here CA 0 1 0. This CA product with A. Again write the third row. Come on. 0 0 0. So 0 0 0 means 0. Next, second 0 0 0 means 0. Next, third column. Come on, 0 1 0 means 1. What is debt? Debt of Q naught equal to 1, not equal to 0. So observable. 99.9% generally they'll ask only check 2 by 2 matrix only. You observe till now there are only 2 by 2 matrices only. 3 by 3 also they don't ask. So just 2 by 2 matrix only they are asking. So one more problem is solved. Just matrix product. If you know, you will get the answer. That's all. Check the controllability and observability. Check the controllability and observability. Check the controllability and observability. Come on. X dot equal to zero, 1, -2, -3, x plus 0 1 u y 1 1 x. Come on, do it. Check the controllability and observability. What is the answer? Is it controllable? Yes. Is it observable? Controllable. but not observable, I think. It is controllable but not observable. Check it. QC. So BAB. B01. AB. So 0 into 1 means 1. Next 0 minus 3. Then that you find minus 1. Not equal to 0, controllable. Next observable. Q0. C is CA. C 1 product with A 1 product. 0 minus 2 means minus 2. 1 plus minus 3 means minus 2. You find that equal to 0 means not observable. That's all. Controllable but not observable. That's all. Next one. Gilbert test for controllability and observability. Gilbert test for controllability and observability. Actually not required, but without any calculation, you can tell the answer. There is a shortcut. Gilbert's test for controllability and observability. Gilbert test for controllability and observability. So this is applicable for only this method. Is applicable for only diagonalization canonical form and Jordan canonical form. This method applicable for only diagonalization canonical form and Jordan canonical form. You should not apply for the what? Remain matrix. If you any other type given, you have to go by column and test only. Okay, na? So note down one problem. For example, I'll take DCF. DCF matrix I'll take. Check the controllability, observability. Check controllability and observability. Here this is multi-input, multi-output system. Check the controllability and observability. Listen. So here this is a diagonalization matrix. It is a diagonalization matrix. Take the first element of diagonalization form. Corresponding to B matrix elements are non-zero. Corresponding to B matrix elements are non-zero. Then it is called controllable. Non-zero. 0 and minus 2 means non-zero. If both are 0, then only treated as 0. Yeah. If both are 0, then it is treated as 0. Even one element presented will treat as non-zero. Even one element presented will treat as non-zero. Even one element presented also, any element, even one element presented will treat as non-zero. We treat as non-zero, whatever the value. That means what? Because of this 2, the states of -2 are going to be changed. Even one input is connected to the states of -2, the states are able to change, then we can say that it is controllable. Similarly, second element of diagonalization form corresponding to B matrix elements are non-zero, then we can say that it is controllable. Then Pura system is controllable. But given matrix must be in the diagonalization form, then only it is valid. Otherwise, 4 times, 2 times controllability you have to check, 2 times observability you have to check. That is the problem. So simply go by this, directly will get the answer. Similarly, take a first element of diagonalization form corresponding to B matrix element is non-zero. Then I can say that it is observable. Similarly, -3 corresponding to C matrix elements are non-zero. C matrix elements non-zero. Then it is called observable. So this particular system is controllable as well as observable. It's a simple shortcut. We remember this shortcut. So that directly we can write the what? Answer. Okay, na? Okay. We can apply Kalman test also, but thing is that 4 times you have to check. 2 times for 2 inputs and 2 times for 2 outputs. Instead of that, this is better, na? You can apply, nothing wrong. Okay. Next. But generally they don't ask, you no need to worry. Till now, single input, single output only they are asking. In diagonal form only, in case if you ask, you go by this method. Okay. Next, JCF, one problem. Next, we'll solve one problem for JCF. Jordan canonical form will solve. JCF. Check the controllability and observability. Check the controllability and observability. Right. You do by yourself. What is there, man? You do it. You take here one more input here. Put it 1 0 or 1 0 something. Put and solve. Already one we solved it. Second time same input you take. For example here 0 1 1 1. You take it. A with this already we solved here controllable. Then with this again check it. You check QC. Simple thing you should do na. 1 1. AB product it. So 0. First enough. First 0. Second one 1. So that means 1. Next here what happened? -2, -2, -3, -5, not equal to 0. That means controllable. That's all. What is there? That 2 times you have to check the controllability, 2 times you have to check the observability. That's all. It is easy only, na? What is the difficulty tell here? You should do now. One thing if I tell, second thing you should try. Again you ask, you do means what happened? You're wasting the time only, na? You do. If you don't get it, then ask me. I given my contact number also. You ask me, no problem. You can call to me also. -2, -2, -3. 1 0 0 0 0 0. Here 0 2 3. Master solved 20% means 80% should solve by students. Then you will get the very good rank. Master solved 100% means students what they will solve. Come on, do it. Only element is 0 in the diagonal form means what, man? What question you are asking, man? S plus 1, S plus 2 is there. Minus 1, minus 2. 0, how it will come? 0 and no element is there. How you will put 0 here? Tell. 3 elements is there. You will get the here minus 3. 4 is there, minus 4. 0, how it will come here? 0. You tell how it will come 0. Practically, you write, take one problem, you write in the diagonal form. How can you get the 0? 1 by S is there is a chance to get the 0. For example, 1 by S into S plus 1 into S plus 2 is there. Then what you will get? You check for that 0 also. That is also Polna. Initial conditions are 0. Initial states are 0. That's all, na? Come on, next. Come on, do it. Is it controllable? Anybody? Come on. Is it controllable? Come on, Guruji. Come on. Is it controllable? Yes or no? Yes, very good. JB is controllable. Is it observable? Is it? Come on. See, listen here. Listen, Bhaiya. This is the Jordan block. So listen, this is Jordan block. This is Jordan block. The last element of Jordan block corresponding to B matrix element is non-zero. Corresponding to B matrix element is non-zero. Then Jordan block is controllable. Then Jordan block is controllable. You should not check the first element, last element of Jordan block, last element of Jordan block, last element of Jordan block, last element of Jordan block. Last element of Jordan block. Corresponding B matrix element is 0. Corresponding B matrix element is non-zero. B matrix element is non-zero. Then it is controllable. Then Jordan block is controllable. For observability, you have to check the similar, okay, -2 completed. Next, check for -3. Just like this is, see, Jordan block is one element in the diagonal form. Just like Jordan block is one element in the diagonal form. Just like Jordan block, one element. That's why only one element is checked. Similarly, check for -3. Here non-zero. Non-zero. That means controllable. That means Pura system is controllable. Similarly, first element of Jordan block, observability, you have to check first element. First element of Jordan block. Corresponding C matrix element. C matrix element is non-zero. Then Jordan block is observable. -2, check it. Non-zero. Non-zero. Observable. So both are controllable as well as observable. That's all. It is controllable as well as observable. Okay, na? It is observable only. Okay. Right. Next. Next one. So this is about the controllability and observability. Actually, one topic is there. In ECE, there is no single question on this topic. Even EEE also, there is no question in the gate. But in IES once asked, this is state variable feedback gain controller. Actually, it is not in syllabus, but very rare cases they are asking the questions on this. So just I'll cover it is state variable feedback gain controller. State variable feedback. Generally, they'll say SVFB, state variable feedback gain controller. In IS conventional and electrical, 2 times they asked on this topic. That's why I'm discussing this. Okay. Right. Tomorrow 6 to 9. Tomorrow control 6 to 9. Maximum tomorrow I'll discuss the questions as well as for electrical people that mechanical systems are there. Even in instrumentation people also we can attend. Process control sir will cover. Still you can attend it. Okay. I'll just within an hour I'll complete for the electrical and instrumentation students, that is mechanical systems. For EC not required. EC just tomorrow will solve the problem so that syllabus will complete. Some problems I'll solve, that is in volume 1. That's all. If you are able to solve by yourself, no need to attend. You will see syllabus if you completed today, tomorrow only problem solving. Otherwise, you have to attend tomorrow 1 hour or half an hour class. At the end, I'll tell. Next purpose. First, listen the class. Forget about when syllabus complete, when this, all that. Listen the class. Purpose. To get the desired location of pole. To get the desired location of pole. This is the objective of state variable feedback gain controller. In this method, all the state variables fed back to the input. Fed back to the input U of the system through specified gain. through specified gain as shown in figure. What they will do, the state variables bring back to the input through gain of k. That's why they call state variable feedback through the gain of k. State variable bringing back through gain. So I'll draw the diagram for example. What is the state? What is the state equation? X dot equal to ax plus bu. You draw the diagram for that. For example here, this is 1 by s. If I take 1 by s, here what is there? X. Here what is there? X dot. So I want x dot equal to ax plus bu. That means I'll take here summing point. I'll take here plus. Here I'll take a. Even this is called state diagram. Now what I am getting? X dot equal to what? Ax. Here u. Here b. Plus. Now you write x dot. What you are getting? Ax plus bu. Then y equal to what? Cx. That means here c. Here summing point. Here y. That means what you are getting? Y equal to cx plus du. From this, you'll connect here d. Then write equation y, cx plus du. So this is called state diagram. In this state diagram, what they are going to do? They are going to be take a one feedback. The state variable x is get fed back through gain k. K is called what? SVFB gain controller. K is called SVFB gain controller. This fed back to the input u with negative feedback. Then here taken some input, V of t or R of t, whatever it is. So this is the diagram for what? State diagram. This is called state diagram with the SVFB controller. So now you write the equation here. So what is u tell? U equal to from figure. What is u tell? Minus kx plus v, where k is SVFB gain controller. That equal to k1, k2 and so on. K equal to k1, k2 and so on. Next, x dot equal to what? Ax plus bu. X dot equal to what? Ax plus bu. Come on, you substitute it. X dot equal to what? Ax plus bu. What is u tell? Minus kx plus v. Now get the answer. Come on. Come on. Get the answer. X dot equal to what? Ax minus bkx plus bv. This can be written as, come on, x dot equal to a minus bk into x plus bv. This equal to x dot equal to acx plus bv. This is called state equation. State equation with SVFB controller. So now, what is AC? Where AC is a state matrix. AC is state matrix with SVFB. with SVFB controller. And what is AC tell? A minus BK. AC is called A minus BK. You have to remember this here. Mainly you have to remember U minus KX plus V. Next you have to remember AC. Next you have to remember characteristic equation. Det of SI minus AC equal to 0. These three remember enough. Det of SI minus AC equal to 0. Characteristic equation. Det of SI minus AC equal to 0. Roots of characteristic equations are poles. That's all. Mainly remember U, AC as well as characteristic equation. These three are enough. Just remember these three. Okay, na? Remember these three. Right. Come on. Note on the problem. For the system specified below, design an SVFB gain controller. SVFB controller such that the closed loop poles of the system are located at S equal to -2 plus or minus J4. Write the state model. X dot equal to 0, 1, 0, 0. X plus 0, 1 U. So listen, solution. First, what you have to find? AC. AC equal to what? A minus BK. So find it A 0, 1, 0, 0. Minus B means 0, 1. Next 2 by 2 matrix, not 2 gain controller you have to take. That is K1, K2. Now do this. Come on, 0, 1, 0, 0, minus, come on, 0 into K1 means 0. 0 into K2 means 0. 1 into K1 means K1. 1 into K2, K2. So what is the answer you are getting? 0 minus 0, 0. 1 minus K1 minus K2. So this is the AC, A minus BK. Next find the what? SI minus AC, characteristic equation. Det of SI minus AC equal to 0. Simply add S diagonally. Add S diagonally means here S and take opposite sign. S plus K2 and take opposite sign. -1 plus K1. equal to 0. Come on, get the answer. S into S plus K2 plus K1 equal to 0. That means what is the characteristic equation? S square plus K2S plus K1 0. For given data characteristic equation, you write. For given data. What is the characteristic equation? Tell. S plus 2 na? S plus 2 minus J4 into S plus 2 plus J4. Come on. What I can write? A minus JB, A plus JB. A square plus S plus 2 whole square plus 4 square. Correct na? S square plus 4S plus 20 equal to 0. Compare these two. Compare. K1 equal to 20. K2 equal to 4. That means K equal to 24. That's all. This is the answer. Okay, na? Two bases kada. Here, how many variables are there? 2 by 2. K is called. What is K I told? What is K here? K1, K2, K3. Based on number of state variables, that many elements you have to take. I told na. 2 by 2 matrix. I told it 2 by 2 matrix. I should take two state variable. To gain controller, I should take. That is what K1, K2. Yes or no? Got it na? If it 3 by 3 is there, you take the 3. Okay? Right. I told it already. Next. One more problem. Note down one more problem. Control process is represented by the following equation. By the following dynamic equation. dx1 by dt equal to minus x1 5x2 dx2 by dt minus 6x1 plus u y equal to x1. The control is obtained through state feedback. U equal to minus kx1, k1 x1 minus k2 x2 plus r, where k1, k2 are real constants. Where k1, k2 are real constants. And r is reference input. Find values of k1 and k2. Find values of k1 and k2 such that zeta equal to 0.707 and omega equal to state feedback means immediately you should have an idea that there will be a gain controller. State feedback means immediately there should be idea that here also there is a word of what they mentioned, state variable feedback means immediately should get the idea that we have to consider gain controller K. K is nothing but K1, K2, K3, K4. What is the order of state variable? State matrix you have to see. State matrix 2 by 2. That means you have to consider two gain controllers. Like that you remember. Okay? You should identify like that. Right. Come on here. First write the state matrix. First write the state model, all of you. Write the state model, all of you. Write the state model. This can be written as what? Tell x1 dot equal to what? Minus x1 plus 5x2. Come on, this can be written as what? x2 dot equal to minus x1 plus u. And now write the matrix x1 dot x2 dot. Come on. x1 x2 plus u. x1 dot linked with x1 minus 1, x2 5. Input 0, x2 dot with x1 minus 6, x2 0, input 1. And y 1 0 because y linked with only x1. Next u also given. U equal to what? Minus of k1, k2, here x1, x2 plus 1 into r. What is u equation? Tell u equal to what? Minus kx plus r. And what is k here? Where k equal to what? Tell k1, k2. Now get the answer. First find what? AC. Next find det of SI minus AC. Come on, do it. All of you do it. Come on, Guruji. Come on. Find AC. AC. Come on. Right. AC. Come on, Guruji. AC equal to what? A minus BK. A. What is A? Minus 1, minus 1, 5, 6, 0. Minus B. 0, 1. K. K1, K2. Come on, solve it. Minus 1, 5, 6, 0, minus 0, 0, K1, K2. 0 into K1, 0. 0 into K2, 0. 1 into K1, K1. Like that. K2. Now tell what is the answer. AC equal to what? Minus 1, 5, 6 minus K1 minus K2. Is it minus 6 or 6? Minus 6 now, okay. Minus 6 minus K1. Now calculate SI minus A. Det of SI minus AC equal to 0. Characteristic equation. Come on. S plus 1 minus 5, 6 plus K1, S plus K2 equal to 0. Now come on, expand this. S plus 1, S plus K2 plus 30 plus 5K1 equal to 0. What is the characteristic equation? S square plus K2S plus S plus K2 plus 30 plus 5K1 equal to 0. So characteristic equation is S square plus S term, take it common, 1 plus K2 plus 30 plus 5K1 plus K2 equal to 0. Next, for given data, so characteristic equation tell S square plus 2 zeta omega ns plus omega n square 0. Bolo S square plus 2 into zeta. Zeta how much? 0.707, 10. 7, 14.14, I think. How much, man? So the given characteristic equation, right, 2 zeta omega n, 2 zeta 0.707 into omega n, 10 into S plus omega n square means 100 equal to 0. Come on, solve it. 1 plus K2 equal to, how much you will get this? 14.14, I think. 14.14, I think. Then K2 equal to what? 13.14. Next, 30 plus 5K1 plus K2 equal to 100. Then find for K1 equal to how much? 11.37. That means K equal to what? 11.37, 13.14 is the answer. That's all. Okay. 22 no. K2 not 22. K2 13.14, I think. Check it. K1 11.37. Okay, na? So with this, state space analysis completed. Next, go for compensators. Today I'll complete the compensators. I'll try to, we'll see time. Controllers also will see. If not possible, controllers will discuss tomorrow. Right. Next, compensators. Compensators and controllers. Actually, for EC, only compensators are there. Controller not in syllabus. For EEE, both are there. Instrumentation also both are there. So compensators and controller. Purpose. But listen, both compensator, controller, even EC students also. Compensators and control. Purpose. What is the objective tell? If the system is unstable, then required a compensator and or controller. A compensator or controller to make it stable and achieve required performance. Achieve required performance or specifications. Even if system stable also, we require sometimes compensators to get the desired performance. If the system is stable, then also required a compensator or controller to get required specification. Sometimes stable, but it is not giving required specifications, means you have to go for compensator controller. Required specifications. Controllers are easy as compared to the compensators. So industry generally they'll use the only controllers compared to compensators. But generally compensators are they are using to get required frequency domain specification generally. Controllers are generally they designed to get the required time domain specifications. But both you can interchange compensator controllers. Controllers easy compared to compensators. That's why industries they'll use only controllers as compared to compensators. Sorry, next one. Listen. See, as order increases, system order type especially as the type increases, generally the system become unstable. So any system, first of all, any system unstable means how to make it stable, tell. If system is unstable, system is unstable, then first what you have to do, how to make it stable? How to make it stable? Come on. If system unstable, then how to make it stable? The first thing what you have to do, you know? What you have to do, anybody? Add zero, change gain, add pole. Addition of pole still will become unstable. Addition of pole still the system become unstable. Addition of zero, one way it is what? Increase the stability. Increase the stability. Addition of zero, increase the stability, but the addition of pole becomes less stable. First step, we have to add a negative feedback and try to make it stable. First priority, anywhere system unstable means they will add the negative feedback. If it is not possible with the negative feedback, they'll adjust the gain. Adjust system gain. Negative feedback as well as system gain, both they will use. If these two are failed in case, then with the negative as well as adjusted gain, and third step they'll add a compensator and controllers. First two are failed, then only they'll go for either compensator or controller. This is the order of the priority to make the system stable. This is the order of the priority of using or applying or adding to make the system stable. Taken a first priority negative feedback. Second one is adjusting the gain. The last priority adding the compensator control. By using about 1 and 2, if it is not stable, then only have to go for the what? Compensators and controller. Generally type 2 and higher order systems are unstable. Type 2 and higher order systems are unstable. For example, see, listen bhaiya. For example, listen. Type 2 and higher order systems are usually unstable. See, for example, I'll take G of S equal to, I'll consider 1 by S square into S plus 2 into S plus 4. What is the type tell here? I'll take H of S1, unity feedback I consider. That means what is the type here? Type 2. It is a type 2 system. It is a type 2 system. I taken type 2 system. So what happened? Is it stable or unstable? Tell. If I write a characteristic equation, what I will get? 1 plus g of s equal to 0. 1 plus g of s equal to 0. So then what I will get? Tell here, characteristic equation if I take. First even 2 repeated poles, it is unstable. I added negative feedback. I added, put it k also, no problem. Put it k, because we'll adjust the system gain also. Put it k. So first k by s square means repeated poles unstable. To make it stable, first I added negative feedback. Now I'll write the characteristic equation. What is the characteristic equation? S for 4 plus 6s cube plus 8s square. Numerator added na plus k equal to 0. So s power 1 term missing here. S power 1 term missing. That means it is unstable. Closed loop system also unstable. You take any value of k 0 to infinity. It is unstable. That means feedback is failed. Adjusting k also failed. There is no alternate other than adding a what? A lead compensator or PD controller. Generally, any system unstable means, if the system unstable means generally add a lead compensator or PD controller. For example, to understand easy, I'll take a PD controller, for example. PD controller I will add. What is the transfer function of PD controller? What is the transfer function? KP plus KDS. KP plus KDS. Okay, na? PD controller I added. KP plus KDS. So now add it G of S with controller. G of S with controller means K into and added 0. That's all. KP plus KDS. We studied in the root locus effect of addition of poles and zeros. Adding 0 means PD controller only. Adding 0 means it's just like adding a PD controller only. Now come on. H of S1. H of S1. Now what is the characteristic equation? Tell. S power 4, 6s cube, 8s square plus k KDS plus k KP equal to 0. That means system is what? Stable. We'll select the k, KD, KF, KP values such that system is stable. So that means here first two are failed. That's why we go for the what? Compensator controller. But when you go for type 1, type 0 system, to make it stable, we don't require any compensator controller. In type 0 and type 1 system, if you want to make it stable, we don't require any compensator controller. So simply with negative feedback as well as with negative feedback system gain adjustment, we can get the what? We can get the stability. Listen. Type 1 system. In type 1, type 0 system, the stable operation is achieved by adjusting system gain with negative feedback. For example, I'll take type 1 system G of S equal to K by S into S plus 2 S plus 4. It is marginal stable system, for example. H of S1. What is the characteristic equation? Tell. S cube plus 6s square plus 8s plus k. So now what happened? Negative feedback with k. K is what is the range of k? 0 to 48. You take any value of between 0 to 48, closed loop system stable. That means here for stability purpose, no need to add any compensator controller. In case type 2 and higher order systems especially, you have to add a lead compensator or PD controller. So in general, in general, type 2 and higher order systems, type 2 and higher, type 2 and higher type systems or higher order, whatever it is. Higher type or higher order, you can write, no problem. Type included in order, na? Higher order systems. In general, type 2 and higher order systems are unstable. In this case, it is essential to add lead compensator or PD controller to make it stable. In type 0 and type 1 systems, the stable operation is achieved by adjusting system gain with negative feedback. By adjusting system gain with negative feedback. Okay. So generally type 2 and higher order, we require the what? A lead compensator or controllers. Okay, na? Next, first we'll discuss the compensators. Next we'll go for the controllers. Next, compensators. First we'll go for the compensators. What is a compensator? Anybody? What is a compensator? It is a simple RC network which adds the finite poles, finite zeros to the system. A compensator is a simple RC network. Is a simple RC network which adds a finite pole and finite zeros to the system at required location. At required location. Okay, na? Next, there are three types of compensators. There are three types of compensators. First one, lead compensator. Second one, lag compensator. Third one, lag lead compensator. Some books, lag lead, lead lag, they used to interchange, but generally practically we'll use lag lead only, lag lead compensator. Theoretically we'll discuss it, but generally they'll use only lag lead compensators. Okay, na? First, I'll explain one simple tabular form, simple shortcut to remember, to easy answer the objective bit. So first I'll discuss that, then we'll start the lead compensator. Okay, na? Right. First, listen. On tabular form, I'll make it. Lead compensator, lag compensator, lag lead. Space lag lead. Okay, theoretically, I'll discuss about lead lag also. There is a small difference. First step here, filters. They use task filters. Which filter it is? High pass, low pass. I'll draw the border plot. No need to worry. Filters. Lead compensator. Leading means going higher. Lead means going higher level or lower level. Going higher level. That means it is high pass filter. Be remember, simple logic. Why? Because if you go by procedure, you have to find the transfer function to the network. After that, you have to draw the border plot. Sometimes they use the lead compensator is, they will ask. That's why simply leading, going higher. So that means it is high pass filter. High pass filter. That means as the frequency increases, magnitude increase. This is high pass filter. Lag means going down. That means it is low pass filter. As the frequency increases, the magnitude is decreases. This is called a lag compensator. So lead means high. Lag means low. Lead means high. Lag means low. So lag low. Lead high. So now if I draw it here, lag lead means low and high. First low, cascade with high. Low and high. First low, go draw low pass filter. Then high pass filter. And which filter it is? Band stop filter. Band stop filter. BSF. Lead lag. Lead means high. Lag means low. That means first draw the high. First draw the eye like this. Cascade with low. The which filter it is? Band pass filter. Band pass filter. Band pass filter. So high pass filter, low pass filter, band stop filter, band pass filter. So like this you have to identify the filters. Like this you have to identify the filters. Okay, na? Right. Next, they will ask the pole zero order. They will ask the pole zero order. Pole zero order. Lead, bolo. Lead means positive angle. Lead means positive angle. Leading means positive angle. Positive angle given by pole or zero, tell? Zero. Positive angle given by 0. That means first 0 should be there, next pole should be there. First 0, next pole. Near to origin, 0 should be there. Next pole should be there. Lead means positive angle. Simple shortcut. Easy to remember, I am telling. No, sir, I will go by procedure means enjoy it. I will tell after some time. I will draw the network, we will find transfer function, we have to represent pole zeros. Time consuming. That also I will discuss. But simple logic to answer. Lead means positive angle. Positive angle given by 0. So first 0. Next, lag means negative angle. Lag means negative angle. Negative angle given by pole. That means first pole, next 0. That means first pole, next 0. That means first pole, next 0. This is called lag. Next, lag lead you are telling me means time constant of lag must be greater than time constant of lead. Then only it is called lag lead. When you are calling a compensator lag lead means time constant of lag must be greater than time constant of lead. That means what is the pole zero order tell? First lag should be there because largest time constant. Next lead should be there. Next lead should be there. Lag. Lag means first what happened? Lag negative angle. Negative angle means pole. next 0. Lead means first angle. That means first 0. Next pole. First 0, next pole. Next, lead lag means time constant of lead must be greater than time constant of lag. Time constant of lead must be greater than time constant of lag. So that means first lead will come. Largest time constant near to imaginary na. Next lag will come. Lead first positive angle 0 pole. Lag negative angle pole 0. Like this pole 0 order you have to remember. You should remember the pole 0 order. They are asking the questions on pole 0 order. You observe the previous GATE and IAS questions. Pole 0 order they are asking. Even one question they asked in the GATE exam. Linked question asked on this. Okay. Linked question asked on this. So one question. Problem. The transfer function of a lead compensator is the transfer function of a lead compensator is S plus A by S plus B. The A and B values are option A -1 -2, option B -2 -1, option C 1 and 2, option D 2 and 1. Come on, get the answer. What is the answer, anybody? What is the answer? C. A. C. A, C. See here, if you say A, it is wrong. If I substitute here -1 -2, it will become what? S -1 by S -2. That means wrong. Right side poles on 0. Answer C correct. So S plus 1 by S plus 2. Because so S plus 1 by S plus 2 means first 0 -1 pole -2. So answer C is correct. Answer C is correct. So you remember pole 0 order. Then substitute the value and then check it. Don't do the mistake. Easy question. So like this question they are asking. Second bit they asked what is the maximum phase lead. How to find that will come later. Okay. Now I'll start the lead compensator. Lead compensator. Tell when sinusoidal input is applied to a network, when a sinusoidal input is applied to the network, it produces sinusoidal output having phase lead. Sinusoidal output having phase lead with respect to input. Then the network is called lead compensator. Then the network is called lead compensator. Okay. Lead compensator is a high pass filter. Which improves the high pass filter, improves the what? Speed, transient behavior. which improves the transient behavior. I told already. Which improves, high pass filter what? Improves the transient behavior. Means speed and stability. Now draw the lead compensator. R1, C1, R2. It is a lead compensator. This is a lead compensator. Now, what you have to do? You have to find the transfer function. Any compensator that gives first step, you have to find transfer function. Second step, poles and zeros. You have to adjust into time constant form. Transfer function should be adjusted into time constant form. Third step, poles and zeros in the S-plane. Poles and zeros in the S-plane. Fourth step, you have to draw the Bode plot. Fourth step, you have to draw the Bode plot. Fifth step, you have to identify filters. Sixth step, omega m at what frequency maximum phase lead occurs. Magnitude at omega m, that we have to discuss. So these are the 6 steps we have to discuss. Come on, first find the transfer function. Come on. Find the transfer function. Laplace of capacitor is what? 1 by SC. 1 by SC1. Come on, first find the transfer function. Simplify this parallel combination. Simplify this parallel combination. Come on. So what I will get? R1 into 1 by SC1 by R1 plus 1 by SC1. Then what you will get? R1 by SC1 R1 plus 1. Then find the transfer function. V0 of S by VA of S equal to impedance across output R2 by total circuit impedance R1 by SC1 R1 plus 1 plus R2. R2 into 1 plus SC1 R1. R1 plus R2 into 1 plus SC1 R1. This is the transfer function. Convert into time constant. Still adjust into. Now this can be written as V0 of S by VA of S equal to R2 into 1 plus SC1 R1 divided by R2, take it inside. R2, take it inside. That means what I will get? R1 plus R2 plus SC1 R1 R2. This can be written as R2 into 1 plus SC1 R1 divided by R1 plus R2, take it common. Then what I will get? 1 plus R2 by R1 plus R2 into what? SC1 R1. ठीक है ना? Take R1 plus R2 common है यार. ठीक है. Let alpha is called lead constant. That equal to R2 by R1 plus R2, which is less than 1. Alpha, let alpha is called lead constant, that is R2 by R1 plus R2. Tau is called lead time constant. Lead time constant. Bolo, what is that? R1 C1. R1 C1. Now substitute in the transfer function. Substitute in the transfer function. V naught of S by VA of S equal to this total. What I can write? Tell this total alpha I can write. This is tau. This total alpha. This is tau. That means what I can write? Alpha into 1 plus tau S by 1 plus alpha tau S. 1 plus alpha tau S. This is the what? Transfer function. This is the transfer function. Now tell alpha. The main drawback of lead compensator is alpha. This alpha creates the attenuation in the system. Alpha is less than 1. So, for example, if some system is there, for example, gain having K. To this connected this lead compensator, what happened? That K is going to be product with alpha, then it will become K alpha. In case K is 10, alpha less than 1, like 0.1, for example, then gain will become what? 10 into 0.1 means 1. That means gain of the system is dropped by the factor of alpha. That is the drawback. The main drawback of lead compensator is it creates the attenuation in the system. Attenuation means gain is reduced. But compensator controller should not reduce the gain. Gain should not reduce. Just it should give the what? Desired specifications. It should improve the performance. Not that increasing or reduce the gain. Gain is reducing. That is the problem. So, but it should not reduce the gain. Then what you have to do? So this alpha should get cancelled. How can we make it cancel? We have to add a amplifier in series to the compensator. So the lead compensator, this is one of the drawback of lead compensator. The lead compensator creates attenuation, adds attenuation in the system. Add attenuation. To the system. Add attenuation to the system. To eliminate the attenuation, required to add an amplifier. Required to add an amplifier to the series of the system. Required to add an amplifier in series to the system. So like this, then alpha will get cancelled. Here they will add a amplifier with the gain of what? 1 by alpha. So that alpha is getting cancelled. So that alpha will get cancelled. Then what is the transfer function? Tell here. V naught of S by VA of S equal to what? 1 plus tau S by 1 plus alpha tau S. That's all. So now what happened here? Because of added amplifier, 1 minute. 1 minute just. Because of the amplifier, right? Because of added amplifier, the cost increases. The cost and number of components are increases. That is one of the drawback of what lead compensator. That is one of the drawback of lead compensator. Okay, na? That's all. Now, what is the transfer function? 1 plus tau s by 1 plus alpha tau s. 1 plus tau s by 1 plus alpha tau s. So now represent the poles and zeros in the S plane. Now represent the poles and zeros in the S plane. Come on, Guruji. V naught of S by Vi of S equal to 1 plus tau s by 1 plus alpha tau s. Come on. Represent the poles and zeros in the S plane. Come on. So simply alpha less than 1, na? Tau is same. Come on. So first what will be there? Tell. See, alpha less than 1. Tau is same. For example, take alpha less than 1. Take 0.1. Greater than 1 means 10 you take. Alpha 0.1. That means what is the pole location? What is the zero location? Yes, z equal to minus 1 by tau. Yes, z equal to minus 1 by tau. Sp equal to what? Tell. Alpha is 0.1. Come on. Minus 1 by 0.1 tau. That means what? Minus 10 by tau. That means first 0 is there. That is minus 1 by tau. Next pole is there. Minus 1 by alpha tau. Simple logic. Lead compensator. Lead means first lead positive angle. Positive angle means 0. Lead means first. We remember positive angle. Positive angle means 0. Next pole. That's all. Simple logic. Now draw the Bode plot. Come on, draw the Bode plot. Draw the Bode plot. Magnitude in dB. What are the corner frequencies? 1 by tau, 1 by alpha tau. This is omega. This is 0 dB. What is initial slope? No poles and zeros at origin. No poles and zeros at origin. So initial slope is 0. Initial slope is 0. At 1 by tau, what is there? 0. 0 means plus 20. At 1 by tau, 0. 0 means plus 20. 0 means plus 20. Yes or no? 1 0 na? Bode plot hai. 1 0 plus 20 dB for decade. Next at 1 by alpha tau pole. Pole means minus 20. Minus 20 plus 20 becomes 0. Which filter it is? High pass filter na? High pass filter. High pass filter. Next, draw the phase plot. Take the projections of corner frequencies. 0 means here also 0. I told just convert the slope into phase angle. 0 means 0. Plus 20 means plus 90. Plus 20 means plus 90. 0 means 0. Then draw it. Select the midpoint and draw a smooth curve. This is called pi m. This is called pi m. This is what? Magnitude at omega m. Here omega m. Omega m is the frequency at which maximum phase lead occurs. 1 by tau, 1 by alpha tau. Magnitude at omega m is 10 log of 1 by alpha. The derivations not required, be remember. Magnitude at omega m is 10 log of 1 by alpha. Maximum magnitude m max equal to 20 log of 1 by alpha. Alpha less than 1, 1 by alpha become greater than 1. Omega m is the frequency at which maximum phase lead occurs. Omega m is the frequency at which maximum phase lead occurs. At which maximum phase lead occurs. Omega m equal to root of first corner frequency into simple logic second corner frequency. Root of, what is the first corner frequency? 1 by tau. What is the second corner frequency? 1 by alpha tau. Then omega m equal to 1 by tau root alpha. Radians per second. Omega m equal to 1 by tau root alpha. Be remember this. Omega m equal to 1 by tau root alpha. Next, maximum phase lead. Maximum phase lead or maximum phase angle. Maximum phase angle. Or we can say lead. Phi m equal to, be remember this formula. Sine inverse of 1 minus alpha by 1 plus alpha. Sine inverse of 1 minus alpha by 1 plus alpha. Sine inverse of 1 minus alpha by 1 plus alpha. You want in tan inverse of 1 minus alpha by 2 root alpha. Generally, they are giving in sine only. Most of the books are given sine. You want cos, you convert it. That's all what is there. What is the range of pi m? Tell. Lead means greater than 0, greater than or equal to 0, less than or equal to plus 90. But ideally, it cannot give the 90 degrees. Ideally, it cannot give the 90 degrees. Ideally speak, it is greater than 0, less than 90 only. Less than 90, maximum plus 90. So greater than 0. This is about the lead compensator. Next, effects of lead compensator. We'll discuss or break. Effects we'll discuss or we'll take break. Right. We'll discuss the effects, then we'll take the break. Okay. Effects of lead compensator. Effects, another 5 minutes, and we'll try lead compensator. Effects of lead compensator. You tell what are the effects of lead compensator? Come on. First step already I told. Lead compensator is a high pass filter. Lead compensator is a high pass filter. Lead compensator is a high pass filter. So what is the advantage of high pass filter? Bandwidth increases. First, identify filter. Bandwidth increases. Next, as bandwidth increases, what happened? Tell. Noise enter into the system. Noise added to the system. Or noise enter into system. So what is the drawback? Tell. Signal to noise ratio is going to be what? Noise added means signal to noise ratio is going to be decreases. SNR decreases. So poor performance. Until less accurate. We can say less accurate. One way you can say less accurate. Okay, na? Next. Noise effect is there in the output. Next tell. Next. Come to the speed. bandwidth inversely proportional to the rise time. Bandwidth increases means rise time decreases. That means quick response. Quick response. Quick response. Lead compensator gives the quick response. Not only TR, here TS also decreases. TR and TS both same. TS also decreases. So that's why quick response. It is quick response. It gives the quick response. Next, bolo. Fourth one. So bandwidth decrease, rise time decreases means quick response. Next, and that means transient performance improved. Transient performance improved. Transient performance improved. Transient performance improved. Next, added finite zero. Yes or no? Added finite zero. Added finite zero. In the transfer function numerator, finite zero is there now, 1 plus tau s. Added finite zero. Any system added finite zero to the any system. Just add finite zero. Blindly we can say that relative stability improved. Addition of finite zero means blindly we can write that relative stability improved. Added finite zero. Relative stability improved. Even the pole added, zero is added means relative stability improved. That's all. Relative stability improved. That means indirectly gain margin and phase margin improved. Gain margin, phase margins are improved. Gain margin and phase margins are improved. Next, what I can write? Added finite zero means zeta increases. For example, see. For example, listen. I'll take 1 by S into S plus 1 I'll take. For example, you consider. Okay, na? What is zeta tell? You consider this is GH, for example. What is closed loop transfer function or H of S1 you consider? 1 by S square plus S plus 1. What is zeta tell? Zeta is omega n, 1 zeta is 0.5. I will add finite zero in the numerator. 1 plus tau s added, for example, by S into S plus 1. What is closed loop transfer function tell? 1 plus tau s by S square plus S plus 1 plus tau s. That means what you are getting, 1 plus tau s by S square plus S into 1 plus tau plus 1, omega n 1. And the zeta increased by the what? 1 plus, what is zeta now? 1 plus like tau by 2. That means it is added tau. That finite zero term, this S term going to be added in the denominator. Addition of finite zero is there means blindly we can write that zeta increases. Added finite zero, blindly can write. Added finite zero. Hence damping ratio increases. Hence zeta increases. Zeta increases. Zeta increases means blindly we can write it what? Percentage of MP decreases. Percentage of MP, not only that, MR also decreases. Both are same na, MP, MR, both are decreases. And the system become less oscillatory. System less oscillatory and more relative stable. That's all. More relative. Like this you have to write. First identify filter, you write SNR. Next, rise time. 2, 3 factors will come with filter. Remain 2 factors will come with added finite zero or not. That's all. Automatically we can write the effects. No need to mug up any effects. Don't mug up. If mug up, we'll get the confused. Lead, lag, PD, PI, PID. So many things are there. You will get confused. So that's why like this, you do the analysis, it become very easy. Okay, na? Okay, na? Yes, we can add alone zero. PD controller added only zero only. But in compensator added pole as well as zero. In compensator, added pole as well as 0. Okay, take the break. After the break, we'll discuss. Okay. Right. Not steady state error increases, the error due to noise, that is going to become more. Okay. Additional noise signal will be there in the output. Noise effect is there in the output. Next, go for lag compensator. Lag compensator. Kanin, we'll close the compensators today and we'll start controllers also. But controllers, I think it won't complete. Controllers will close tomorrow. Tomorrow 6 to 9 or 9:30 I will take. 6 to by 7 o'clock, 7 or 7:30, I'll close the syllabus for EC. And after that, I'll take for electrical. After the break, I'll take for electrical. I'll close syllabus by 9 or 9:10 like that. Okay. So next, lag compensator. When sinusoidal input is applied to a network, when a sinusoidal input is applied to a network, it produces sinusoidal output having phase lead, having phase lag with respect to input. Then the network is called lag compensator. The network is called lag compensator. Lag compensator is a low pass filter. Which improves steady state performance. Which improves steady state performance. Come on, now draw the lag compensator, all of you. Tomorrow 6 p.m. I think. They given schedule 5 p.m. Tomorrow 5 or 6? 5 p.m. mentioned already. As I know 6 p.m. I'll find out. You told it taken, man. Takes from 6 p.m. onwards. It will take 6 p.m. No problem. Okay. 6 p.m. onwards I'll take. Okay. Right. Next, draw the network. R1, R2, C2. So this is 1 by SC2. V naught of S. VA of S. Find the transfer function. V naught of S by Vi of S equal to R2 plus 1 by SC2 divided by R1 plus R2 plus 1 by that equal to SC2 R2 plus 1 by बोलो SC2 into R1 plus R2 plus 1. Now this can be written as one plus SC2 R2 divided by 1 plus. So what I can write R1 plus R2 into SC2. Multiplied and divide with R2. Multiplied and divide with R2. Okay. Let alpha is lag constant. That is alpha 1 plus R1 plus R2 by R2. R1 plus R2 by R2, which is greater than 1. For lag compensator, alpha is greater than 1. Tau is lag time constant. R2 C2. V naught of S by Va of S equal to. What I can write here? This is called alpha, this is called tau, this is called tau. 1 plus tau S by 1 plus alpha tau S. 1 plus tau S by 1 plus alpha tau S. That's all. Represent the poles and zeros. What is the zero location? Minus 1 by tau. What is the pole location? Minus 1 by alpha tau. Alpha 10. In case alpha 10 means what? Minus 0.1 by tau. That means first pole is there. Alpha greater than 1, na? So first pole minus 1 by alpha tau. Next 0 minus 1 by tau. Now draw the plot. Draw the plot. This is omega. First corner frequency 1 by alpha tau. Next corner frequency 1 by tau. So this is 0 dB. Initial slope is 0 because no poles and zeros at origin. So initial slope is 0 up to 1 by tau. Next at 1 by alpha tau, what happened? One pole. One pole means minus 20 like this. One pole means minus 20. Minus 20 dB for decay. Next at 1 by tau, 1 0. 1 0 means plus 20. Plus 20 minus 20, 0. That means low pass filter. It is a low pass filter. Now draw the phase plot. Take the projections of corner frequencies. 0 degrees. Initially 0. Then minus 90. 0. Select the midpoint. Draw the smooth curve. This is called pi m. This is omega m. So magnitude at omega m is what? Same formula, sir. No difference at all. Only alpha value change. Magnitude at omega m is 10 log of 1 by alpha only here also. 10 log of 1 by alpha. Alpha is what? Here greater than 1. 1 by alpha become less. Automatically negative magnitude you will get. Here magnitude minimum, not maximum. Yeah. Here we'll say magnitude minimum. Minimum magnitude how much? M minimum here. M minimum is 20 log of 1 by alpha. 20 log of 1 by alpha. Minimum magnitude. Lag compensator gives the maximum magnitude of 0 dB. Minimum is negative. Omega m is the frequency at which minimum phase angle occurs. Omega m, the frequency at which minimum phase angle occurs. Minimum phase occurs. Omega m equal to root of first corner frequency into second. Same thing, 1 by tau root alpha only. Radian per second. Even minimum phase. Pi m equal to same thing, sine inverse of 1 minus alpha by 1 plus alpha only. Alpha greater than 1. Alpha greater than 1 means by default you will get the negative angle. Alpha greater than 1, na? So alpha greater than 1 means by default you will get the negative angle. And what is the pi m range? Minus 90 to 0. Minus 90 to 0 degrees. That's all. That's all. Okay, na? That's all. Next. Okay. Nothing happens, but transfer function should be satisfied. That's all. You want to use inductor, but generally they don't use inductor. It is more costly, more noisy. There are many drawbacks. When you are getting a response with better element, why will you go by inductor? Yeah? It is more bulky. Right, next. Effects of lag compensator. Come on, write the effects by lag compensator by yourself. Lag compensator is a low pass filter. Lag compensator is a low pass filter. Hence bandwidth is reduced. Second one, as bandwidth is reduced, noise is eliminated. As bandwidth decreases, noise is eliminated. Hence signal to noise ratio improves. Signal to noise ratio improved. Third one. As bandwidth decreases, race time is increases. Not only that, TS also default increases. So slow response. Speed decreases, na? slow response. Next, added finite zero. Here also added finite zero na 1 plus tau s numerator, but finite zero is leftmost here. Added finite zero. Added finite zero means relative stability improved. Lead also improves the relative stability. Lag also improves the relative stability. Both are improving stability. In case stability affected, then we don't use the what? Compensator at all. So lead lag also improving stability, but slightly increases. It is slightly increases. Generally, lag compensator when you will use, if the system is less unstable, slightly unstable, preferable is lag compensator. A system is more unstable with more poles, right? Generally preferable what? Lead compensator. So generally slightly unstable with zeta slightly negative, less than 0, slightly negative, then prefer the what? Lag compensator. Generally, lag compensator is preferred. Here gain margin and phase margin improved. Both are improves gain margin and phase margins. You want to check it in the booklet. Gain margin, phase margin improved. Lag compensator preferred if the system is slightly unstable. Lag compensator is preferred. If the system is less unstable. Or having low negative damping, small negative damping. The zeta negative slightly. That's all. Next, fifth one. Gain margin, phase margin improved. Next, added finite zero. What happened? Already I told, zeta increases. Percentage of MP decreases. System more relative stable and less oscillatory. As compared to lead compensator, it may be little bit more oscillatory. But both are improves the what? Relative stability. Lag is slightly improves relative stability. Lead is improved by large amount. Be remember this. Okay, na? Right. Next go for lag lead compensator. One more thing here, steady state performance improved. That word it didn't write. Lag compensator improves the steady state performance. Already I written in the starting. Right. Next, lag lead compensator. Why we need lag lead compensator? Why we require lag lead compensator? Lag for steady state, lead for transient. Both you want to improve, you have to go for lag lead compensator. So lag lead compensator improves the transient and steady state performance. One problem we'll solve before this. Note down one problem. We'll solve one problem. Right. The lead compensator the lead compensator and its transfer function as follows. Is as follows. Transfer function is s plus 1 by s plus 10. Sorry. Here it is 1 microfarad. Find the following factors. Find following factors. First one, R1 and R2 values. Second one, the frequency at which maximum phase angle occurs. The frequency at which maximum phase occurs. Ante lead. Third one, maximum phase lead angle. Come on, do it. Come on, solve. So what is the transfer function? Tell. 1 plus s by time constant form if you write 10 into 1 plus 0.1 s. 10 you can eliminate. So 1 plus s by 1 plus 0.1 s. Compare with standard form. 1 plus tau s by 1 plus alpha tau s. That means what is tau? 1. What is alpha? Alpha tau equal to 0.1. That means alpha is 0. Now get the value of R1 and R2. Tau equal to 1. That equal to what? R1 1 micro. R1 C is 1 micro, na? 1 micro. Then get the answer of R1. 1 by 1 micro. That means 1 mega ohms. This is R1. Next, find R2. Alpha equal to what? R2 by R1 plus R2. Which is nothing but what? 0.1. So 0.1 equal to R2 by 1 mega plus R2. Now solve this. To solve this, 0.1 mega plus 0.1 R2 equal to R2. Then solve for R2. You will get 311.11 kilo ohms. So R1 R2 value हो गया. Next second bit omega m equal to what? 1 by tau root alpha. 1 by tau 1 alpha is 0.1. That means root 10 radians per second. Third one pi m sine inverse of 1 minus alpha by 1 plus alpha. Sine inverse of 1 minus alpha is 0.1 by 1 plus 0.1. Sine inverse of 0.9 by 1.1. You solve it, you will get 54.9 degrees. That's all. Like this, you have to solve. Okay, na? Right. But in the, you follow only these formulas, but in some books, either you observed or not, they given transfer functions of the compensator. Here, transfer function of the compensator either lead or lag. What I taken? 1 plus tau s by 1 plus alpha tau I taken. But in some books, what they did, transfer function of compensators they taken, either it may be lead or lag. What they taken is 1 reverse they taken, and 1 plus alpha tau s by 1 plus tau s taken. Either it may be for lead, it may be for lag. So in case in the exam, they don't give, till now they didn't give in the GATE exam. Till now they didn't give. In case anywhere you observe like this transfer function, don't think that it is wrong. It is also 100% correct. But here, be remember, the alpha values are going to be changed. Alpha. So how to identify means simply be remember lead compensator. Listen, how to identify alpha value means lead compensator. First, what should be there in the lead compensator? What should be there in the lead compensator? Tell first. Positive angle 0, next pole. What is 0? Minus 1 by alpha tau. Minus 1 by tau. So first we should get 0 means, we should get 0 near to origin means, what should be the alpha value? Tell. Alpha should be greater than 1 for lead. Alpha should be greater than 1 for lead. For lag compensator, they don't ask. In case if you ask it, be remember. Represent pole 0, from that you identify the alpha. Or alpha in the numerator reverse to the what we discussed. So here what happened? Lag compensator. First pole next 0. Minus 1 by tau. Minus 1 by alpha tau. Because some books are given like this. That is the problem. So 0 should come leftmost means alpha should be less than 1. Then lag. What about formulas? Formulas will be same. Omega m 1 by tau root alpha only. Radians per second. Pi m is, what is the formula for pi m? Sine inverse of alpha minus 1 by alpha plus 1. Sine inverse of alpha minus 1 by alpha plus 1. That's all. Even if we compare, for example, we take in our problem, na? That problem compare same answers you will get. So what is the transfer function? 1 plus s by 1 plus 0.1 s. Na? You compare same answer you will get. 1 plus alpha tau s by 1 plus tau s. You compare answers will be same. That means what is alpha? 1. What is alpha tau? Alpha tau equal to 1, alpha 1, tau equal to 0.1. No. So alpha tau equal to how much? 1. Then tau equal to how much? 0.1. That means alpha becomes what? 10. Alpha become 1 by tau means 10. Now for example, get omega m, same answer, 1 by tau root alpha. So what is 1 by tau? 0.1 into root alpha, root 10. This can be written as what? 10 by root 10. What is the answer? Root 10. Answer not going to be changed. Even pi m also same. Sine inverse of alpha minus 1 means 10 minus 1 by 10 plus 1. Same answer. Sine inverse of 9 by 11. Same thing, 54.90. And the answers are not changes. But you remember only what we discussed. This is just for objective type exam. anywhere objective type exam, in that they are asking the formulas like Genco, Transco, some exams, local exams, they are asking formula. Once asked this formula, PIM formula asked, the transfer function of the lead compensator 1 plus alpha tau s by tau s, then the phase lead angle they ask. Another thing, remember, lead means we should get the positive angle. Positive angle, alpha greater than 1. So alpha greater than 1, then only will get the positive angle here. This is only satisfied. So be remember this alpha in the numerator, then sine inverse of alpha minus 1 by alpha plus 1. Alpha in the denominator, sine inverse of 1 minus alpha by 1 plus. You don't remember this. You remember that. Other than that comes automatically take this. You cannot be remember. Whatever it is, be remember, mention lead compensator means the angle should be plus, positive should get. The sine inverse of the value should be positive. So lag compensator they are mentioning means angle should be negative. That means sine inverse of bracket function should be negative. So that you be remember. Okay, na? You be remember. Okay? Next, go for lag lead compensator. Lag lead compensator. Lag lead compensator improves the lag lead compensator improves the transient and steady state performance. Transient and steady state performance. Transient and steady state performance. We don't require, most of the time they'll ask either lag or lead only, but not mixed. Some textbook they didn't give about this lag lead also. They given either separately lag or lead. Just I'll give the brief idea. We don't require more than this. V not VI. This combination for leading, this combination for lag. The transfer function is, we don't require more than this, 1 plus tau 1 s by 1 plus alpha 1 tau 1 s. Even textbooks also they didn't give much. 1 plus alpha 2 tau 2 s. This is for lead. This is for lag. You don't find transfer function also. Just be remember. Here remember pole zero order and filter. That is more than sufficient. Remember 4-0 order. Lag lead compensator means tau constant of lag must be greater than time constant of lead. Be remember. That means tau 2 should be greater than tau 1. So pole zero order you represent. First should be what? Lag. Next should be lead. In a lag, first what? Lag means pole. So minus 1 by alpha 2 tau 2. Next is 0, minus 1 by tau 2. Lead means 0, minus 1 by tau 1. Next pole, minus 1 by alpha 1 tau 1. Now draw the Bode plot. Zero dB. First 1 by alpha 2 tau 2. Next 1 by tau 2. Next 1 by tau 1. Next 1 by alpha 1 tau 1. So what happened initially? 0 na? First no pole and 0 at origin. So initial slope is 0. Initial slope is 0. Next at 1 by alpha to tau to 1 pole. 1 pole means minus 20. Draw minus 20. This is minus 20. Next at 1 by tau to 1 0. 0 means plus 20. Plus 20 minus 20 becomes 0. So this is 0. Next again 1 by tau 1. At 1 by tau 1, 1 more 0 means plus 20. Next pole means 0. So which filter it is? Band stop. Now draw the phase plot. Take the projections of corner frequencies. Zero degrees. Initial slope 0. Minus 20 means minus 90. 0 means 0. Plus 20 means plus 90. Just 0. Select the midpoint and draw a smooth curve. Lag lead means at low frequency lagging is there, at high frequency leading is there. Lag lead means at low frequency lagging, at high frequency leading is there. That's all. This is about compensators. Next, go for controllers. Next, controllers. Controllers. Come on. A controller is a device which is used to control the transient and steady state performance. Control the transient and steady state performance. As per requirement. A controller is a device which is used to control the transient and steady state performance as per the requirement. As per requirement. Okay. The best system demands first one, smallest raise time. Smallest settling time. Smallest peak overshoot. Smallest steady state error. Smallest steady state error. To get the above requirements, we require to add a controller in series to the system. The block diagram with the controller is as follows. The block diagram with the controller is shown in figure. Controller. System. Unity figure. This is a block diagram. Okay. So the controller input is error E of t. Right. Next one. First, proportional controller. Proportional controller. Come on, do it. Proportional controller. What is the objective? What is the purpose? What is the purpose? To change the transient response. To change the transient behavior of the system. By changing system gain. By varying system gain. To change the transient behavior of the system by varying system gain. That's all. Okay. Now, transfer function of proportional controller is transfer function of P controller. P means proportional. Controller equal to Kp. Transfer function of proportional controller is Kp. For example, listen. For example, G of S without controller, I'll take 1 by S into S plus 10. 1 by S into S plus 10. H of S equal to 1. What is the closed loop transfer function tell? 1 by S square plus 10S plus 1. What is omega n? 1 radian per second. Find zeta 5. That means system is overdamped system. System is overdamped. Zeta equal to 5. System is overdamped. Now with controller I'll take G of S with controller. With controller means what happened? Kp by S into S plus 10. In series, na controller in series. Series to the system. So Kp is product. H of S 1 only. What is the closed loop transfer function tell? Kp by S square plus 10S plus Kp. So for example, I'll take Kp equal to 100. What is omega n? 10 radians per second. What is zeta? 0.5. That means what happened? We changed overdamped to what? Underdamped. Whatever the nature you want, we can achieve simply by changing the K value. By varying the K value, we can get the required transient response. By varying K value, Kp value, we can get required transient response. By varying Kp value, we can get required transient response. But what is the disadvantage? What are the disadvantages, advantages? What are the effects of proportional controller? Here no pole added, no zero added. Just increasing the gain. Increasing the Kp value means increasing the gain of the system. Increasing the gain of the system. What is the gain here? 1 by 10. Open loop gain, not closed loop gain. Increasing the open loop gain of the system. 1 by 10 is the gain. Here Kp by 10. Kp increases, open loop gain is increases. What are the effects? First effect already I written. Transient behavior. That is main objective. That you leave it. Next tell. Proportional controller decreases the steady state error, but it cannot eliminate the complete error. For example, say G of S equal to 1 by S into S plus 10. H of S 1. What is the error for ramp input tell? What is the steady state error for ramp? A by K na? For ramp input. For ramp input. Unit ramp input, for example. So A is 1. What is K tell? Numerator constant by denominator. 1 by 10 means 10 is the error. If in case I'll take with controller, what I am getting? Kp by S into S plus 10. H of S1. Now tell what is the error? ESS, A by K. A is 1. K is what? Kp by 10. That means what you are getting? 10 by Kp. If your Kp increases, what happened? Tell error. It will become 0. If Kp very, very large, Kp infinity means it becomes 0. But Kp should not take infinity. Kp should not take infinity. The system may become unstable. Kp become very, very large, the system may become unstable. That's why the proportional controller decreases the steady state error, but not eliminated completely. Write that word. The proportional controller is decreases steady state error. But not eliminate completely. proportional controller decreases. Proportional controller decreases steady state error, but not eliminate completely. Second one is, in case Kp go on increases, omega n is increases. Numerator increase, omega n. Default zeta decrease. Zeta decrease means percentage of MP increases. That means system become less relative stable. And more oscillatory. And more oscillatory. Less relative stable and more oscillatory. Next, bolo. Omega n increases means even slightly bandwidth decreases. Omega n increases means slightly bandwidth increases. So slightly, not large. Because again zeta decreasing, na, that's why. Bandwidth increases slightly. So that means race time decreases. That's all. That's all. No more factors. So these are the effects of what? Proportional controller. Any more, anybody? Right. Right, next. Practical circuit. Practical circuit for a proportional controller. Practical circuit. This is VI R1 R2 minus plus R V0 R. Actually, this is just inverter. It is inverting amplifier because it is gives the 180 degrees phase shift. We require to connect the second stage inverter just to eliminate the 180 degrees phase shift. The main controller is first one only. What is capital? V0 of S by VA of S equal to Kp. That equal to what? Tell R2 by R1. Here minus R2 by R1 into minus 1 means it will become R2 by R1. Generally R2 is variable. It is like 0 to infinity. R1 is fixed. That means we can get the what? By varying simply R2, we can get the required value of Kp. By varying R2 value, we can get the required value of Kp. That's all. This is the practical proportional controller. Practical diagram for the proportional controller. Okay. Next. Go for derivative controller. Next. Next, derivative controller. PID kada, integral controller kada. Next. Integral controller. Integral control. Integral or other word is what? Reset controller. Integral or reset controller. Purpose is to decrease steady state error. to decrease steady state error. Integral or reset controller purpose is to decrease steady state error. Transfer function of integral controller is I controller. Ki by S. Transfer function of integral controller is Ki by S. What happened in integral controller? Tell one pole added at origin. Integral controller added one pole at origin. Added one pole at origin. Hence type of the system increases. Hence type of the system is increases. As type increases, steady state error is decreased. Type is greater than input. Steady state error becomes 0. For example, G of S if we take 1 by S into S plus 10. H of S1. But what is the problem? Here, steady state error decrease, but system becomes less stable. But system becomes less stable or unstable. That is the problem. Type, today only I told type 2 and higher order systems are usually unstable. I told today only. That is the problem. For example, check it. What is the characteristic equation? Tell S square plus 10S plus 1 equal to 0. 100% stable system it is. Next, with controller you take. What happened? Tell Ki by S you should add and S square into S plus 10. Then H of S equal to 1. What is the characteristic equation? Tell S cube plus 10S square plus Ki equal to 0. System what happened? Unstable. Why? Because S power 1 coefficient missing. S power 1 coefficient missing. So type increased here. Here what is the type? 1. Here what is the type? 2. Type increased means error should be reduced. But problem is system become what? Unstable. Unstable system, we don't calculate steady state error at all. Once it become unstable, we never calculate the steady state error. Steady state error calculated to only closed loop stable systems. That's why before connecting integral controller, it should verify the stability. If the system is stable, then only integral controllers are used. Otherwise, integral controllers are not used. Before connecting integral controller, it is essential to check the system stability. Before adding integral controller, it is essential to check the system stability. Check the system stability. If system stability affected, if system stability is affected, then integral controllers are not used. Then integral controllers are not used. Integral controllers are not used. Compulsory you should check the stability. ठीक है ना? Draw the practical circuit. Come on. This is the controller. This is inverter. Now find transfer function. Laplace of capacitor 1 by SC. V naught of S by VA of S equal to minus minus become plus. Z2 by Z1 minus 1 by S by R. So that means 1 by SCR. That equal to 1 by tau YS. That equal to KI by S. Where KI equal to 1 by tau Y. That equal to 1 by RC. Next effects you write. Write the effects. Integral controller is a what? Low pass or high pass? 1 by S means minus 20 slope. It is a low pass filter. Integral controller is a low pass filter. Hence bandwidth is decreases. Hence bandwidth decreases. As bandwidth decreases, rise time increase means slow response. Even TS also default increases. Next, as bandwidth decreases, noise eliminated. Noise eliminated. Signal to noise ratio is going to be improved. Steady state performance improved. Low pass always steady state performance and accuracy improved. Fourth one, no addition of finite zero. Is there any finite zero here? No. No addition of finite zero. Less relative stable. Less related. The gain margin, phase margin decreases. Damping ratio zeta decreases. Zeta decreases. Percentage of MP increase. Less relative stable, more and more oscillator. That's all. These are the effects of These are effects of what? Integral controller. Derivative we'll discuss, then we'll close. Another 5-10 minutes. Okay? Okay, na? We'll discuss the derivative and then we'll close. Okay, derivative controller. Same thing, 2 minutes only. It will complete 5 minutes. Okay, derivative controller. Purpose is to improve the stability. 5 minutes only. Purpose. Actual controller not in syllabus for EC, but still listen. Derivative controller to improve the stability. To improve stability. Transfer function of derivative controller is KDS. What is the statement tell? Added 0 at origin. Hence, type decreases. As type decreases, what happened? Tell? Stability improved. S means stability. Stability improved. Stability improved. But as type decreases, steady state error as type decreases, steady state error increases. Steady state, that is the problem. That's why practically even they don't use derivative controller also. Another word for derivative controller is rate controller. So for example, G of S equal to, I have to take unstable system and I have to make it stable. S square into S plus 10. In just 5 minutes only. Type 2 system. Characteristic equation S cube plus 10S square plus 1. Unstable. Closed loop system unstable. S power 1 term missing. With the controller, if you take KDS by S square into S plus 10. 1S cancel. That means type becomes 1. Characteristic it becomes S square plus 10S plus KD. System becomes stable and stability improved. But type decreased and error may increase. Less accurate. That is a problem. And even derivative controller is does not respond if error is suddenly changes. If error changes suddenly, then derivative controller is does not respond. Write that word. Derivative controller does not respond. Derivative controller does not respond. Does not respond to sudden change in error. To sudden change in error. This is called anticipatory error. This is one of the drawbacks. This is called anticipatory error. The system will hang it, that's all. It does not respond. That is the problem. Draw the practical circuit. Completed, Landy. So that tomorrow we'll discuss PI controller, PD controller, PID controller, so that syllabus will complete for ECE, and then I'll solve some problems in volume 1. Frequency domain analysis questions I'll solve. Now come on. You try to solve who are not solved. At least frequency domain analysis questions. Inverter, here product is -1. First one, controller. Transfer function tell V0 by Vi equal to R by 1 by SC. That means SCR, that equal to tau ds, that equal to KDS, where KD equal to tau D, that equal to RC. You tell the effects, man. Effects by yourself you tell. 0 means high pass filter, na? Yes or no? Derivative controller is a high pass filter. Is a high pass filter. Hence bandwidth is increases. As bandwidth increases, noise added. So SNR decreases. As bandwidth increases, rise time decreases. Quick response. Performance effects means what? Speed, accuracy given by noise, speed, and stability. That's all. Next, added 0 at origin. Added 0 at origin. Addition of 0 always improves the stability. Improves relative stability. Zeta increases. Percentage of MP decrease. More relative stable, less oscillatory. That's all. That's all. With this, I'll close. If you have any doubt, you can ask. Come on. Right. I'll close here. If you have any doubt, you can ask. You can write the hand. Agarwal.
Hello, sir.
Tell man.
Sir, my doubt is in slide 12.
Tell.
Sir, in it, as सर कल जैसा अपन ने डिस्कस किया था कि जॉर्डन स्लाइड में
जॉर्डन उसमें
ओके सर एंड सर इन जीसीएफ बी मैट्रिक्स विल बी 1 जेबी ब्लॉक
repeated poles means above that one should be there na,
but
in
sir,
B matrix you are telling here 1 na.
Yes,
it may be 1 or other constants also possible. Standard
yes,
representation means it should be 1. Just like BC matrix coefficient, they will adjust na, like a diagonalization canonical form.
Yes, sir.
Like that they'll adjust so that you may get it other than 1 also.
Then, sir, all matrices will be controllable in JB form.
How can you say here if it 0 is there, is it controllable? For example, I'll put here 0. Is it controllable?
But, sir, how it is possible?
Why not? The examiner, if he gives the 0, then what he will do?
Okay, but practical, sir, as in transfer
Practical
function.
unstable systems are not exist and then won't be there. Uncontrollable means no connectivity at all. Na input to system, no connectivity means you don't get output also. You cannot check the stability. Practical systems are what always controllable as well as observable, because there should be a path from input to states and states to output. Na?
Yes, sir.
This is just theoretical analysis only. Na?
Okay, sir.
Okay, na? Right.
Okay, sir. Thank you.
Next, Abdul. Abdul.
Hello sir,
tell.
page number 16.
Tell.
సార్ ఇది మనకి K1 ప్లస్ ఇప్పుడు K1 K2 అంటే ఇప్పుడు ఇది చెప్పారు కదా సార్, ఇది కంపెన్సేటర్ సార్.
కాంపెన్సేటర్ కాదా ఇది?
కంపెన్సేటర్ కాదు,
ఎస్విఎఫ్బి ఫీడ్బ్యాక్ గెయిన్ కంట్రోలర్.
ఇవి ఈసీ వాళ్ళకి ఏది అంటే గేట్
ఈసీ వాళ్ళకి అడగలేదు ఇప్పటిదాకా. దే డిడ్ంట్ ఆస్క్ ఎనీ క్వశ్చన్ ఫర్ ఈసీ టిల్ నౌ. In IES last year they asked conventional question for 10 marks. Actually it is not in syllabus, but they asked. IES state space analysis itself not in syllabus, but in the gate, even IES subject, there is no single question on this topic.
Okay sir. ఇప్పుడు కంట్రోలర్ కాంపెన్సేటర్స్ అవి కూడా అడుగుతారా సార్? అంటే అంత ఇంపార్టెంట్ కాదా గేట్?
Very rare.
Okay.
Read up to state space. Compensator controller, very rare cases. Okay, controllers not in syllabus, but last 2 years onwards controllers not there. They didn't ask any question on controllers. Compensator in syllabus.
Okay sir. ఇప్పుడు lag lead చెప్పారు కదా సార్, lag lead కంపెన్సేటర్ ఒకసారి.
Lag lead generally they don't ask because many books are not given about lag lead.
ఇప్పుడు కంపెన్సేటర్స్ లో మనకి ఆల్ఫా వాల్యూ ఏది అంటే బెటర్? ఆల్ఫా గ్రేటర్ దెన్ 1 అంటే క్రిటికల్లీ డాంప్డ్ చెప్పారు కదా సార్.
క్రిటికల్ డాంప్డ్ కాదయా,
స్టేబుల్.
alpha is less than 1 lead, greater than 1 lag. The transfer function is 1 plus tau s by 1 plus alpha tau s. If transfer function is reverse, alpha value going to be reverse.
Okay.
Okay. Next.
Hello, sir.
Karthik.
Sir, sir, in DCF and JCF, do we need to consider the in DCF and JCF, do we need to consider repeated fall at first? Is it like that?
Nothing like that. We can write it even second also.
Okay.
Okay.
Order can be varied, right?
Anything. Okay.
Okay, sir. Thank you.
Next, Naga Nitesh.
Good evening, sir.
Good evening, Chappamma.
Sir, 8F. Sir, ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్?
ఏదిదా?
Yes, sir.
Uncontrollable means this input is there, na?
Yes, sir.
Input use, this input signal should not reach to x1.
Okay, sir.
That means this should be 0, na?
Yes, sir.
0 into u means no signal comes here.
Yes, sir.
And k plus parallel, na? K plus 1 must be equal to 0.
Okay, sir.
K equal to -1.
Yes, sir. సార్ దాని తర్వాత జస్ట్ లైక్ చెప్పారు కదా సార్, మోర్ పాత్స్ ఉంటాయి అప్పుడు.
More?
మీన్ అదే ప్రాబ్లమ్ లో సిగ్నల్ ఫ్లో గ్రాఫ్ లో మోర్ స్టేట్స్ ఇంక్రీజ్ అవుతాయి.
More paths అంటే for example here they put -1.
Yes, sir.
In case here -1 is there.
Okay, sir.
As per the condition, what they told, if the signal flow graph given to check the controllability, observe the path from input to states.
Okay.
Path exists, controllable. Here looks like path, na?
Yes,
one
sir.
path 1, one path -1. And path exists, you will write controllable, but it is wrong. Why? Because the resultant you have to see -1 + 1 becomes 0.
Okay. We need to
That's
check.
why instead of physical verification, what I am telling, you write ABC matrix for this.
Okay.
Then use the column test.
Okay, sir.
That will be the better. ठीक है ना?
Okay, sir. Understood, sir.
Okay, अम्मा.
Thank you, sir.
Okay. Next, Abdul.
సార్ ఇప్పుడు ఇది కంట్రోలబుల్, మనం కంట్రోలబుల్ ఇంకోటి చెప్పారు కదా సార్ అబ్జర్వబిలిటీలో, ఏ సిస్టమ్స్ కి మ్యాట్రిక్స్ కి మనకి కరెక్ట్ వాల్యూ వస్తా లేకపోతే సిగ్నల్ ఫ్లో గ్రాఫ్ కి అంటే ఏది పాత్ మనం
Kalman test के correct వస్తది.
కాల్మన్ టెస్ట్ కినా?
Use the
Kalman-
Kalman test always.
ఓకే సార్.